I would like to continue with the fundamental theorem of line integrals. We introduced it in the last section where I actually called it fundamental theorem for line integrals. It doesn't matter. Okay, in the last video, actually, we talked about it, not the last section. It's still the same section. So let's do some examples. But before we do the example, let me explain what the fundamental theorem of for line integral is again. So if f is conservative, that means we can have a phi such that f is a gradient of phi. Okay? If this is true, then there is a quick way of computing the line integral along C. The line integral along C can just be computed as phi at B minus phi at A, right? Where A is the beginning point of C, the curve, and B is the final point of C, the curve. Okay? And then, if f is conservative, then the line integral along any closed curve is just 0. Okay? Does that make sense? All right. So, but one thing we have to also know is that if the right hand side is true, if we can find phi such that phi of A minus phi of B is the same thing as the line integral, then we know that f is conservative. Okay. All right. So let's do an example. Let me look for a quick example that is also clear. So the first example we're going to do is has to do with a line. Okay, let f be the line integral or the vector field y squared I plus 2xy plus e to the 3z j plus 3y e to the 3z k. And we would like to evaluate C. Actually, evaluate the integral along C of f dr, where C is a simple curve from A is 1, 1, 0 to B, and B is 2, 1, 0. Okay. The hint here, I'm gonna give you a hint. The hint is f is the gradient of phi, where phi is equal to xy squared plus y e to the 3z plus some constant. Let's call that constant, well, just don't worry about that. Okay. In other words, f is conservative. So in this problem, we're given that f is conservative, so that means there exists a phi such that gradient of phi is equal to f. And we actually know the phi in this case, and we're asked to compute the line integral, right? Along the line segment, or along the curve, the simple curve from A equals 1, 1, 0 to B equals 2, 1, 0. Okay. So it doesn't matter what the curve is. We are given that C is a simple curve. So we have the point 1, 1, 0. I'm going to draw one, 1, 0 is going to be somewhere here. That's A, 1, 1, 0, and 2, 1, 0. So 2, 1, 0. It's somewhere here. B, 2, 1, 0. Okay. This is our y-axis, and this is our x-axis, and that's our z-axis. So we're going along this curve, a green curve, any green curve, right? It could be that curve. It could be a green curve that goes like this. So this could be our C, and it could be, sorry, let's use pink, use another color. It could be this pink color. It doesn't matter as long as it starts from A and ends at B. Okay? Or it could be another curve altogether. Think of maybe let's make it black. Think of another curve that starts here and ends there. Okay. So it's just any curve, any simple curve. Okay. All right. So now we want to use the fundamental theorem of line integral. So our fundamental theorem of line integral, f, we want to compute f dr, which is the same thing as f dot t ds. This is just going to be phi at b minus phi at a. Okay. So why? Because we're using the fundamental theorem for line integral. Okay. So phi is a function x y squared plus y e to the 3z. So let's plug in a. A is 110 and b is 210. So if we plug in b and plug in a and subtract, we get plug in b, we have, let's plug in b. B is 2 times 1 squared plus 1 times e to the 3 times 0, okay, minus 1 times 1 squared, that's for a, plus 1 times e to the 3 times 0. 3, yes, I think that's it. So you can actually calculate this. This is just 2, and 2 actually is 3 minus 2. So our answer here is 1. Okay. Let's try another example. All right. Okay. Line integral here, or the vector field, is 3 plus 2xy I plus x squared minus 3y squared j. We would like to evaluate the integral f dr, where c is the curve generated by r of t equals e to the t sine t I plus e to the t cosine tj, and t goes from 0 to pi. Okay, so what do we have? We have our c, and c goes from r of 0. This is r of 0 here. R of 0, if you plug in r of 0, r of 0 means plug in 0 for t. If you plug in 0 for t in the first component of r, you just get 0, right? And if you plug in if you plug in 0 for t in the second component, you get 1. Now, r of pi would be, if you plug in 0, or if you plug in pi, you actually get 0 for the first component. Plug in pi for the second component, you get negative e to the pi. Okay? Now, using the fundamental theorem for line integral, we know that f dot dr is equal to phi of b minus phi at a. So this is our a, and this is our b. Okay. But now we don't even know that, we're not even told that f is conservative. Okay? So we have to go through the process of checking to see that f is actually conservative. If f is conservative, then we can now find the equipotential function, or the potential function actually. All right, so we'll have to find that f is conservative and find the potential function. But if you recall from previous video, we actually did this from the previous video. So we can recall that f is conservative. We showed it in the previous video, and I don't remember if we actually computed the potential function. I think we did. We actually did. So the potential function is that. Okay. F is conservative, and we got our potential function. So we just need to calculate f dr using the fundamental theorem for line integral. All we need to do is plug in phi at b. B is 0, negative e to the pi. And then plug in phi at a, which is 0, 1. And then do the subtraction. So plug in phi at 0, 0, negative e to the pi. And then plug in 0 and 1. Okay, so if we start with 0 and negative e to the pi, plug in 0 and then negative e to the pi, we get negative e to the 3 pi. Okay, that's what we get for the first one. And then when we plug in 0 and 1 in the second one, we get 0 and minus 1. I think that's what we get. Yep. So my answer is that. negative e to the 3 pi minus 1. I would need you to check my answer for me. I did that in a rush. So if you find any mistake, write a comment. If you're in the class, also tell me in class. But first of all, write a comment so I get it right away and make a comment, make the correction. So let's look at the third example. We have this 3 plus 2xy I plus x squared minus 3y squared j. We would like to evaluate the integral f dot dr, where c is the circle, r of t equals cosine t, sine t, and t is between 0 and 2 pi. My hint here is that the answer is very, very easy. This is the easiest thing you could do, all right? So I want you to try this. You just need to know one thing. You don't need to solve a lot. And I want to mention something. This means that it's a closed curve. The C is a closed curve. So sometimes you see it written as just a circle. Some other times you see it as a circle with an arrow to show the orientation. All right, we're going to stop here. I will see you in the next video.